Welcome to the Intersecting Us podcast, where math and life intersect.
In today's podcast, Brian and Dave discuss the beautiful equation, exploring the elegance of Euler's identity and its real-world renaissance.
What does exponential growth, the sine curve, and imaginary numbers have to do with each other? What if we could imagine and explore a formula that maybe tried to get all those things to come together? Or could it even be done? And we're going to talk a little bit about that today. And Dave, I'm going to bring you in here and talk about a little bit about the value of imagination. We talked about this last podcast about how imagination and math go together. But now we're looking at something even deeper. These different concepts, these different almost disciplines and formula uses is maybe coming together. How does that come about when you're using your imagination and the math that comes behind it?
Sure. Welcome, everybody. It's good to be here. And if you're like most people, the idea of coining imagination and mathematics together seems to be like a far stretch because we're used to thinking of math as very fixed and absolute. And it just seems like it requires memorization, not imagination. And I think that that's what is often communicated in schools, either intentionally or maybe more unintentionally, but often that is the message that's received. And I think that really misses out on a lot of the beauty of math. And so we are talking a lot about how math is a creative work. And we're using the word imagination partly because we've got an imaginary number, I, that, brings that word imagination into the vocabulary of math. And so I think it's appropriate to talk about math and imagination. And, I ran across this quote that I thought was inspiring to me. And so I'd share it with everybody. And it's a quote from a guy named Francis Su. And he wrote a book called Mathematics for Human Flourishing, which is a book I highly recommend for our audience if you're looking for a book that brings the human side of math out. Anyway, here is the quote. Francis says, "Exploration cultivates the virtue of imagination. In order to solve problems, you have to ideate new possibilities." And I think that is something we don't think about with math, that in order to solve problems, you have to ideate new possibilities. We often think that you have to memorize formulas, you have to take good notes, you have to, learn this concept, but you don't have to ideate new possibilities because we're encouraged not to think about new things when we do math often. And so I like this quote because it highlights not only is that something that can be done, but as you get deeper in math, it's a requirement to ideate. And for those who are deeper into math, I'm probably preaching to the choir because they know how important all this is. But for people that are just kind of beginning to get into math, this idea, may be something new. And so that's what our goal would be, to talk about that today.
Well, the term exploration we tend to use to physical sciences, maybe life science, those types of disciplines. I think where we probably, and we have talked about that in past podcasts, that it does seem like you said earlier, Dave, that math is not usually a discipline that a lot of people, associate with exploration. It's the idea that we pretty much have everything we need to be able to use math in our particular disciplines, whatever it may be. But looking at some of the past mathematicians, somewhere on the line, what we have now had to be discovered. And so you don't discover unless you explore. And I think you've done a good job of showing that. And you'll tell us more today about a particular person who did some exploration. And I think that always helps us think, well, maybe there's things now that we think we know maybe all the math there is, but perhaps we don't. And maybe doing some imagination. And I like that word ideate. That's kind of a cool word that Sue uses there. But But I think exploration in math is probably, as you said, something that people who are in math a lot might understand, but probably for the layperson, that's not even something that's on their radar.
Mm-hmm. Right. Yeah. And to put all this in context, we are arriving at a pretty significant destination, Brian, that we should maybe celebrate a little bit, in that we have been on this eternity series for what seems like an eternity, right?
It could be. Depending on how you define that term, yeah.
Yeah. I think we actually started on this about a year ago when we started thinking about putting together videos. And, it took us a while to figure out how to do it. And then when we got done with the videos, and we decided to do the podcast. And so even though we're not like going into nuts and bolts of the Eternity series videos in the podcast, they have been going in parallel. And so the topic for today really coincides with the 7th math video in the Eternity series, the last one. And so, it's been a journey of exploring, what is eternity. And so that's kind of the context of what we're talking about is, we are talking about in eternity and infinity. And in doing so in math, we have talked about the sine function. If you can remember when we first brought that up, one of the things it brings is the number of hours of sunlight in a day. And, we kind of had fun with that. I'm sure you remember that, Brian, right?
Oh, yeah. Yeah, that is kind of a neat, it's one of the things people can see pretty clearly, especially if they live in North America, because we're not on the equator. As things change a little bit, that sine curve makes a difference.
And of course, it's not just that. It's in music. It's all over. The sine function is so much in math and science, and so it's on our calculator. So it's a big deal. And then we talked about E, which is another letter that is a button on our calculator. So it's a big deal, especially for actuaries, but really mathematicians in general. It's the foundation of calculus. So we talked a lot about E, and both the sine function and E have notions and messages that connect to the infinite. And so very two different ideas, but they both connect to the infinite. And so, we talked about those as well.
Yeah, I think when the infinite and the eternal, we're not going to get into that too much. You can look at past podcasts and even those videos, similar, but I think our main difference there we talked about was infinite is a term you use a lot in math, positive, negative, infinity, and all those things. And then eternal, I suppose, is a superset of that, where it includes infinity, but more about, existence and all those types of things. But that's the cool part about it. That's what the Eternity series was always about, is that infinity in math and eternity in life intersect at such a great level.
Mm-hmm. Right. So yeah, we had fun with that. And then the last big topic we brought up was I, the imaginary number. And unlike the sine function and E, where they are kind of like mathematical ideas that come about from either patterns or limits, I is just something we simply defined. It was just something that we imagined as math people. It was a solution to a problem. Eventually, what it did was it gave us a solution to what is x when you have x squared equals -1. Before that was not defined. We brought in I, and then now that has an answer. And so that is I is a totally different animal compared to E and the sine function. Not only in just what problems it tries to solve, but the fact that it is completely an invention of the human mind that we just, decide to come up with the last few hundred years to work on algebra problems. But now it shows up in so many different places because it's one of those tools that has reinvented itself. And so it's a big deal in the math world.
Yeah. And you find that sometimes in exploration. I was reading about, I think it was Coca-Cola was, originally had a low level of cocaine in it and was used as a health elixir, and that's what they were trying to come out with, something to help stomachs and all that. And obviously we don't use that for that anymore. And that's not a perfect analogy, but it is sometimes things that don't seem like they're related. You can relate, but it takes some exploration. That's for sure.
Well, it's funny. I was trying to think of like how to communicate how unrelated they are. And I must admit, talking about cocaine was not anything that came to mind, but that's why I've got you on the podcast too, to bring out those things I'll never think about. But
as I say, well, that'll get people buzzing one way or another, I guess. Hopefully
we may get a bad reputation.
Yeah. Oh God. Yeah. That's it. Drink Coke, not the other. Yeah.
So anyway, where that led in our last couple of videos in the Eternity series was we uncovered what is often referred to as Euler's identity. And, Euler is one of those guys that we talk a ton about and we will continue to talk a ton about. But he came up with this identity or formula, if you want to call it that. And I'll just first of all read it. And the formula is E. And then we're going to raise it to a power. So E raised to an exponent. And the exponent is two things multiplied together. And those two things, surprisingly, are pi and I. And so multiplying pi by I seems like an extremely weird idea to do, because pi has to do with a circle and I is a solution to how to bring in x squared equals -1 into the algebra world. And so those two things really seem like they don't go together at all. And now they're sitting up as exponents to the base E, where E itself is what we call the exponential number. It's an irrational number. It's kind of like a weird number, 2.718. And I know, Brian, you got that memorized about 500 digits. And, it comes about originally when we were looking at compound interest, but basically it has to do with the perfect smooth exponential curve. And so it's like a totally different animal than pi, which has to do with circles, and I, which is a solution to an algebra problem. So all those three things couldn't be further apart in the math world. And yet Euler put them all together and found out that when you take that expression, it comes out to something. And then you add 1 to that. The result, unbelievably, is 0. Which means simply that E raised to pi times I equals -1. And you have to really take some time to really think about that, to really appreciate what a crazy idea that answer is. But it took the math world, by the storm, and they've been kind of like feeding off this idea ever since. This was like the mid 1700s where this idea was identified, but it's been often called like the jewel of mathematics. Some call it the most beautiful equation in mathematics. I've got a book on my bookshelf, and the entire book is doing nothing but unleashing what this formula means and how beautiful it is. And so there's so much to appreciate about this formula. We're not, of course, going to get into the weeds of that, but hopefully we can at least take a moment and appreciate what a beautiful formula this is.
Yeah. And do you have, and you don't have to, do you have any idea of his discovery process on that? Or is that something that you'd ever read, or if you could talk about it at all? Was he trying to accomplish something? Did he have a goal, or was he just kind of playing around with the formulas and see what they showed? Or?
Yeah, I've kind of forgotten some of the details, but I've read quite a bit about it. And so I'm going to try to, I guess, go from my memory. The big idea through it all is, let's take the expression E raised to the X times I. So what we're doing is, rather than using pi 3.14, we're putting in the variable x, where x could be any real number. In fact, it could be any complex number. But for the sake of discussion, we'll keep it simple and just say x can be any real number. So 0, 1, 1/2, pi, all those are real numbers that we can substitute in for x. And so now think about e raised to the I times x. And that's not quite as maybe unusual thing, because now x could be anything, and we're taking that times I. And what happens is this entire expression, e raised to I times x, regardless of what real number you substitute in for x, the result of that expression, when we plot it on a complex plane, it lands on a circle where the radius is 1. And so that seems to be really odd, because if we think of xy in the xy coordinate, we can substitute a value for x, and let's say what the formula we have is some line, then we can put in a value for x, and we can kind of think about the answer for y. It's going to be somewhere on this line. And so as we go left to right on the x coordinate system, the y value, will just be that answer that gets us to a line. And so we are comfortable with that, for a linear equation in the xy coordinate system. But here we're in the complex plane. And now whatever we put in for the value of x, the answer, the y answer, is going to be somewhere on this circle where the radius is 1. And it doesn't matter what value of x it is, the answer is always going to be there. And so that's the real big idea that you need to start understanding when you try to, make sense of that. And I think that's where Euler's mind was unwrapping and uncovering that big idea.
So he was kind of looking at it maybe more of a trigonometry, maybe where he was kind of looking, and maybe it imposed itself as he was playing around with it.
Right. Yeah. And I hadn't thought about that. So if you think about, when you set e to the I x as your starting point, now the right side of that equation has a totally different expression. And that expression that this equals is the cosine of x plus I times the sine of x. And those were pretty familiar functions in Euler's day. And he knew that expression likewise is always going to be a result on the unit circle, regardless of what you put in for x. And so he had something that he knew already was a circular function where whatever value for x you put in, the answer is going to be somewhere on the unit circle using the cosine and sine function. And then he found this new idea where you take e raised to the ix, and he found the same concept. And in fact, those two, moved step and step. And so that's why we can write that the equation e to the ix equals cosine of x plus I sine of x. And so that is the general formula that Euler uncovered that was the big deal for mathematics. And many people will call this really the most remarkable formula, because what happens is if we substitute now pi for x, well, then the left side becomes e to the I pi, which is what we started with. And then cosine of pi is -1 and sine of pi is 0. So the right side then becomes -1. And so we have e raised to the I pi equals -1. And if we want to bring the -1 to the other side of the equation, we add 1 to both sides. And then we finish with what we started with today, which is the specific formula, e raised to pi I plus 1 equals 0. And that's the result we get when we substitute pi in for x.
This is more conceptual, plain mathematics and algebra and trigonometry. And so how did this formula, or has this formula been used, like, I guess we call it the real life, as far as the sciences, it certainly works in math. Mm-hmm. Are there other places that it has use?
Yeah, it's really used a ton in the sciences. It's the foundation for music theory and sound waves, really any types of waves, sound waves, light waves, all those things use this equation as part of its foundation. And if you feel like you kind of have at least a grasp of that both of these produce a circle, then we can take it one more step to identify for a given value of X, where on this circle is the result. Because, I just said that it's going to be somewhere on the circle, but I didn't say where on the circle it is. And so, we can do this, abstractly on a podcast, because I'm going to trust in your imagination a little bit, since it's on imagination. But if you happen to have paper and pencil, feel free to use those now. But if you just draw a circle, and if you think about the circle like a clock, and the hand is pointing to 3 o'clock. So it's, pointing left to right. And so we're at 3 o'clock on that circle. That is the starting point. And so now we're going to go counterclockwise around the circle. And so the next number we're going to go to from 3 would be 2 on the clock, because that would be counterclockwise. And so if we go from 3 to 2, we have made 1/12 of a rotation around a circle, since there would be 12 numbers on a clock. And we went from 3 to 2. That's one number. And so if we go from 3 all the way to 12 o'clock, we took 1/4 of a turn around the circle. And if we go from 3 o'clock to 9 o'clock, we've gone 1/2 of the way around the circle. And if we want to know, well, what is the distance around the circle from 3 o'clock to 9 o'clock? Well, then we need to remember the formula for what is the circumference of a circle. And Brian, I don't know if you happen to remember that. I'm putting you on the spot, but
2 pi r, I think.
Yeah, you're right. 2 pi r. And so here, r is the radius, and that's 1. And so we're multiplying by 1. So we can simplify 2 pi r to just 2 pi. So that is the distance around a unit circle if you go all the way around. But when we go from 3 o'clock to 9 o'clock, we're only going halfway around. So what would be the distance halfway around of a circle if it's 2 pi all the way around?
Just be pi.
Pi. Okay. So that tells us the distance around the circle is pi. And if we look at, well, what is that point on the unit circle? That point is, if we go up and down, that result is 0, because it's on the x coordinate system, and the point it's on is -1. And so the value that we're on the unit circle is actually -1. And so that's where we get -1, is because it's the distance around the unit circle when we put pi in there.
Okay.
And so that principle holds true for all examples of x. And so if we put in, let's say, 0 for x, that means we don't go anywhere. Well, now we are ending up on the point 1, 0. And so that's going to be, an answer of 1. So if you put in 0 into that expression, you're going to get 1. And so you can choose any point on the unit circle, and you're going to be able to identify what is your answer when you plot this in the complex plane.
Okay. So that you can see where it starts as you look at it, and, you wonder maybe if you even put pi in there, and that's where and it worked out that it was 1. And then he's like, well, that's interesting. That has to do with the circle. And who knows how his mind worked. But as we kind of finish up here, what bringing that into kind of, as people are listening, I'm certainly thinking about it, how kind of tying it into our eternity series and all that. You use the term that people call it the beautiful equation, which is an interesting term. You talk a little bit about that, not just maybe the math part of it, but why do they call it the beautiful equation? How does beauty get brought into it?
Sure. And of course, beauty is in the eye of the beholder, but the logic that's often shared is E is often considered one of the most important numbers in all of math. As actuaries, we could say easily it is the most important number, but in all of math, it's certainly one of the most important numbers. In calculus, it's probably the most important number. And so E is a Hall of Fame type number that has so much beauty behind it. And of course, pi, most people have heard of pi. They learn about that in school. And there's even, the pi day. We all kind of identify it as some sort of geeky number. But when you stop and really think about what pi represents, it truly is amazing what that number represents. But it's clearly one of the most important numbers in all of math. So you have E and pi, which could easily be argued the two most important numbers in all of math. And then you have I, this weird fella out there that we just defined. And what I allowed us to do was to expand the real numbers to a broader set of numbers called the complex numbers. And with this new set of numbers, the complex numbers, we can solve all kinds of problems we couldn't have solved before. So I opened up a whole new frontier to mathematics. And so we have these three things that each and of themselves are beautiful numbers and yet totally unrelated to each other, seemingly. And yet they all come together in one formula. And it also produces the number 1 and the number 0. And, the number 0 is popular because we call it the additive constant, which means if you add anything to 0, you're going to get that number. And 1 is the multiplicative constant. If you take X times 1, your answer is always going to be X. And so two of the probably most common important integers are there. So you've got three of the most important numbers that are not numeric, and then probably the two most important numeric numbers, and they all show up in an extremely surprising manner, in a beautiful, clean and pristine manner into one formula. And math people really like simplicity. And I know that goes against what a lot of people think, that math people want complexity, but that's not true. Math people really appreciate simplicity and conciseness. And so this is an extremely concise formula that brings 5 different things together in one wonderful relationship.
And I do see why you would call that beautiful, because as you say, it's in the eye of the beholder, but yet it still has intrinsic qualities that are not just conceptual and ideas, but have reality. And you see this formula used in reality and engineering and chemistry and things like that. So it's not an either or. Is this just conceptual or is it useful in physical world? No, it's both. It has kind of the beauty of have the simplicity, but yet it also has a utilitarian use because it actually works in the sciences, which is, kind of a good way to kind of sum up our idea of eternity and infinity. The concept infinity we use in mathematical concepts to come up and do math on paper, as they say, in our mind. But yet those also, many of them have moved into, exploring space and seeing how, and then talking about that and exploring, neutrons and electrons and getting smaller. And all of a sudden you're getting into how far does this go down, kind of an eternal sequence, which is kind of cool. Mm-hmm. I don't know if this is the right way to put it, but I was thinking about a biblical verse that I've heard at weddings. You could say that how could you put it? You could say, I pi, and e remain, but the greatest of these is e.
I have never heard that before.
You can quote me if you want. I've never heard it before either, but that I just thought that was kind of, you get those three things. I think it's faith, hope, and love.
Right.
To a wedding, but I think that was kind of it kind of thought that both pi and I have such good, but the E is kind of the thing that kind of is the catalyst that keeps it all going. So, well, we're about ready to wrap up. Is there anything else you want to add about this beautiful equation?
Well, I just encourage everyone to take time to think about this. There's plenty of videos we put together. There's other videos on this, but take any of these ideas of E and pi and I and look at them, separately if you want, or you can look at this Euler's identity. It certainly is a wonderful formula to learn more about, even if you don't think you'll ever use this formula, like maybe an actuary probably will never use this formula, but that doesn't mean you cannot benefit from it. And so I would encourage you to take some time and watch some videos that do a great job of explaining why this formula exists and some of the cool nuances that it represents.
Yeah, and I think that's a good summation because it does and it brings in that the beauty part and the even the goodness part, the truth part certainly that we've been talking about. So maybe the best way to end this podcast would be to kind of just quote Sue, that first little phrase that he had, because I do think this helps. I hope it helps people think, whether you're math oriented or not, that discovering and exploring is always a good thing to do and get your mind to think about things in different ways, which I hope gives you some joy too, which is another thing we talked about. So we'll end with this. This is from Francis Sue in his book, Mathematics for Human Flourishing. Exploration cultivates the virtue of imagination.
This has been the Intersecting Us podcast. To further engage with Intersecting Us, go to intersectingus.com.